Hi, and welcome again to my Physics Online video lecture series. In today's video, we're going to be discussing the relationship between heat and temperature, and maybe a little bit about calorimetry experiments while we're at it. So, you'll recall that so far I have introduced temperature. So, let's begin by recalling what it is that temperature is. Temperature is a sort of measure of the average kinetic energy, translational kinetic energy specifically, of a substance. Or of the molecules in the substance. And that's really all that we need to recall to start this off. So the new topic that's being introduced here is heat. And heat is, you could think of it as thermal energy. It is energy that it's not fair to say it just causes temperature changes because it does other things, but for today's purposes, heat is energy that causes changes in temperature or is due to temperature differences. We can represent heat for what it's worth using either an H or a Q, a capital Q. The units for it are, for MKS, the joule, just like any other energy, or also an SI unit, the calorie, C-A-L, calorie. For what it's worth, one calorie is approximately 4.184 joules. What does heat do? Well, we'll get into a little bit more of the details of this in the next set of videos where I discuss the laws of thermodynamics. But for our purposes, heat causes a substance to change its temperature or to change its phase. As we will see in a future set of lectures on thermodynamics, heat can also be used to do work. For today's video purposes, what heat is doing is changing the temperature of a substance. In a future video, I will add in the idea that temperature can also, or that heat can also cause phase changes. Now, the main equation that goes with today's video is to essentially show how does the temperature of an object change with the amount of heat added. So that's kind of our key. And that also applies to heat removed from the object or substance. And the answer is, we're basically just looking at what does it scale with. So let's say that I have two otherwise identical objects, but one of them is a lot larger than the other. The question that I might ask is, if I were to add the same amount of energy, the same amount of heat to both of them, then which one would I expect to actually have a bigger temperature change? So by analogy, imagine that you have a window unit, like a window AC unit or a space heater or something like that, and you're trying to heat or cool a room. Now you have the same window unit and you can put it on a window in one of two rooms. One of them is a small room, like maybe a little bedroom, and the other one is a really large room, like maybe the main family room, living room, dining room area. And you're going to run both of them, use the same amount of energy for both. Which room is going to be more effectively cooled? Well, the answer is the smaller of the two rooms. Why? Because we're doing the same amount of work, and therefore we're able to remove essentially the same amount of heat from both. There's some scaling effects, but essentially you're removing the same amount of heat from both rooms. And if I remove the same amount of heat from a little room as I do from a big room, the little room becomes cooler much more quickly, or much cooler than the big room does. So size matters somewhat. The more stuff you have to heat or cool, the less change in temperature we expect to see. So putting all these statements together, or putting that statement together, I would expect something like delta T to be proportional to 1 over the amount of stuff. Now the amount of stuff, I kind of treated it as if it was a volume of stuff, but that's not a very good measurement. A large room, a small room, that's not a very great measurement. It's actually better to use how much actual air is there in the room, or how much actual stuff in general is there. And as you'll recall from our much earlier video on the Newton's laws on mass and weight, the best measure of how much stuff there is the mass. So I expect a temperature change to be inversely proportional to the mass, or in other words, if I was going to write an equation that has these two terms on it, I expect these two terms to kind of show up on the same side of the equation if we're putting everything in numerators. Okay, secondly, I would expect that the more heat I add or take away, remove from a system, the more the temperature is going to change for that system. So if I had a small window unit and I run it and then I replace it with a much larger window unit, the much larger unit is able to add or subtract more heat from the room, remove more heat from the room in the same amount of time, and we notice that that room ends up being much cooler. So more heat removed means bigger temperature difference. And the same is true if we go the opposite way and say I have a little space heater versus a very big space heater, or a little fireplace versus a big fireplace. Okay, the last kind of term that we need in order to make our equation set up is we need some sort of a scaling factor. So these two equations could kind of go together to say something like heat added or removed should be proportional to mass times temperature change. But we don't want a proportionality, we want an equality. So we posit one last term, which we call the specific heat capacity. Sometimes it's written as a C sub P or a C sub V. Essentially, this is semantics about are we keeping the volume or the pressure of the room constant. I'm simply going to use a lowercase c for specific heat capacity. And once I have done that, then I have a very simple equation that relates amount of heat added or removed to the temperature change of a substance. So this new term that we have here, this is called specific heat capacity. And what it essentially has a value for each given substance. So in other words, if I have something like aluminum, a very good conductor of heat, it's going to tend to have a different, probably lower heat capacity than if I have something like, say, wood or wool, which are relatively good insulators of heat. So this specific heat capacity has units of either joules per kilogram degree C, or joules per gram degree C, or joules per kilogram K, or joules per gram K, or calories per gram degree C, or calories per gram K. Those are all valid units for this thing. And usually we see it in terms of either joules and Kelvin and kilograms, or we see it in terms of calories and grams and degrees C, but any of these combinations are valid, and they're all validly SI units. How the calorie was defined, for what it's worth. So, definition of a calorie. Basically, the definition of a calorie is, it is the quantity or amount of heat to change the temperature of 1 gram of water from 20 degrees C to 21 degrees C. In other words, by 1 degree C. It should be the same amount if we're changing from, say, 29 degrees to 30 degrees, or from 80 degrees to 81 degrees. There are actually slight differences, so we'll use this as like the formal definition and a colloquial definition, which says simply that it is the amount of heat needed to change the temperature of 1 gram of water by 1 degree C, which is also by 1 Kelvin. And again, 1 calorie, 1 cal, is equal to 4.184 joules. So it actually takes 4.184 joules of heat to raise the temperature of water 1 gram worth from 20 degrees to 21 degrees. There's a related thing, which is, what is the specific heat capacity of water? And that, of course, is going to be our first little example. Well, we've already declared that heat should be equal to mass times specific heat times temperature change. That implies that the specific heat should be the actual heat added divided by the mass divided by the temperature change. So for water, we just said that 1 calorie is the heat for delta T equals 1 degree C and M equals 1 gram. It follows that the specific heat for water is equal to 1 calorie per 1 gram times 1 degree C. And so therefore it is 1 calorie per gram degree C. If you'd prefer to put it in joules, this is 4.184 joules per gram degree C, or 4.184 joules per gram Kelvin. If you want to get into kilograms, then seawater, the specific heat capacity for water, is 1,000 calories per kilogram degree C, or 4,184 joules per kilogram degree C or Kelvin. Okay, so that basically just is the specific heat capacity definition for water. There is a related term to all of this, which is the specific heat. And the specific heat basically is the amount of heat needed to heat a specific substance, which includes a mass in that, by a given temperature. So typically it's how much heat would you have to add to this object in order to raise the temperature by 1 degree C. So as an example, how much heat is needed to raise the temperature of 60 grams of water by 1 degree C. That would be the specific heat for that 60 grams worth of water. So for that example, you'd say that heat is equal to mass times C times delta T. So that's 60 grams times the specific heat capacity, which is 1 calorie per gram degree C, times 1 degree C. And so our specific heat, so this will be specific heat for this water, is going to be 60 calories. And that's it, 60 calories, or 60 calories per gram is usually technically the way you want to do it, or 60 calories per, degree C. So sometimes this term right here gets removed to get us from heat to specific heat. That's all for today's video. Thanks for watching.